Alright, I just need some break. Something up with my eyes, I think reacting to the markers or something, or just getting used to it. I don't know, it's also pretty late. Probably shouldn't be doing this right now. I think my neighbors can't hear me through these walls. If they can, then they probably hate me. But anyway, so we proved this thing. And this was the first thing that we really proved, is that we have uniqueness of identities and inverses. Okay. Notation. We will write P of xy equals just xy or x dot y. 1 equal e and x inverse as x inverse. I don't want to write out like the inverse of x. Okay, cool. There. Now I've only used one line because this is really just short. This is going to shorten our notation a lot. So I'm just going to do xy or x dot I. Then e is typically 1. Sometimes it's not. It depends on your mood and who's teaching. But this is also pretty standard, is x inverse being x to the power of minus 1 being the inverse of x. And so, let's see here. Now we have another definition. A group G is commutative or Abelian after the mathematician Abel, who apparently made some contributions and then died really, really young. Something unfortunate like that. I'm pretty sure. Yeah, I'm pretty sure he was like 26 and he was trying to find a job because he was a mathematician and he went, I don't know. And he finally found a job, but he had gotten sick and then he died. I don't know, something like that. So, if for all x and y in G, xy equals yx. And so, we typically write xy equals x plus y, and x inverse equals negative x. Okay, so, and why do we do that? We do that because our typical Abelian group example is just addition. Because we know that if you're adding numbers together, you can flip the order and it's fine. And so that makes it Abelian. And so that's why we write the product or the law of composition as x plus y. And then, of course, x inverse is just negative x, because that's the additive inverse. So let's do an example. Let's see here. Z with plus is commutative. And that's just very basic math. Yeah, if you have m things and n things, it doesn't matter if you add these. Yeah, it's commutative. So that's commutative. So then GL2 C is not. And this is, of course, GL2C, our composition law is matrix multiplication. And that's another basic thing from linear algebra, is that matrix multiplication is not commutative. You can have two matrices, you multiply them one way and it gives you one thing, then you flip the order and you multiply them and you get another thing. I don't have an example handy, otherwise I would do it. Let's see here. We've also got Sn is not commutative. Now, we haven't talked about Sn yet. There's ways of expressing elements of Sn that make it very easy to work with, but we haven't gone over those. If we had gone over those, I'd show you examples to see that this is why this is not commutative. But just as a general example, or just reason why you should expect this, is that elements of Sn are functions, and the composition law, or the law of composition is composition of functions. And generally, compositions of functions are not commutative, because you could think of plenty of functions where you do it one way, you get one thing, and you compose the functions in one direction, you get one thing, and you flip the order of the composition, you get something else. So this is not commutative. Okay? So that's that. So abelian groups are important, and we'll talk more about them later. But for now, we're going to talk about another important idea in group theory. That is going to be homomorphisms. And these, now when we talk about linear algebra, we talk about functions a lot, but which functions do we talk about? We talk about linear functions, because it turns out that linear maps tend to be the ones which are really important in linear algebra. In group theory, the maps that are important are group homomorphisms. So what is this? Definition. Let G and G prime be groups. A group homomorphism, or just a homomorphism from G to G prime is a map, we'll say phi, and it starts in G and it lands in G prime, such that was really rising up there, such that for all x and y in G, now I'm going to think of how to write this. Phi of A. Okay, I guess I'm using A and B. Or sure, let's stick with x and y. Phi of x dot y is equal to phi of x dot phi of y. Now, what's important here is to keep track of these dots. What are these dots? These dots are the composition laws of the groups. But where are they taking place? Phi, of course, is a function of G. And so this whole thing inside here is an element of G. And so this dot here between x and y, this dot is the composition law in G. So we could write it as dot sub G. This dot is between phi of x and phi of y. Phi maps G into G prime, so phi of x and phi of y are both elements of G prime. And so therefore this product is the composition law in G prime, and so you can denote it by that. In general, if you want it to be extremely clear, you would always differentiate between a product in G and a product in G prime. But generally, it's just too much work. And like if you see here, I wrote this really small G here, and it's really hard to see, and it's really hard to write that small. And homomorphisms are so important, and they come up so much that if we did this every time we had a homomorphism, it would be really cumbersome. And another thing that's really important is that it's also good for you to not include this, because every time you see a product, you have to think to yourself. You have to think, oh, where is this composition taking place? And being able to keep track of where these compositions are taking place is going to just generally make you more intelligent, because you're using brain power. Every time you see a product, you have to think, oh, where is this happening? And then you look at the things around it. Oh, these things live in G prime, so we know the product is G prime. Here, these things live in G, so we know the product's in G. And it's really good, and you start to get really good at it, and you get stronger mentally. So that's that. Let's see here. So lemma. Also, we sometimes write phi is in hom G comma G prime. That's a little bit more of an advanced notation. If you get, like I'd say after this course, people typically start learning about category theory. And when you get into category theory, things like hom spaces, these are very important. So this notation comes up a little later down the line usually, but we can start using it now here if we want. In fact, I might use it because it makes things easier to write. So actually I'm going to start right now with that. So let phi be in hom G comma G prime. So here again I'm condensing a lot. I'm saying a lot of things here. I'm saying let G be a group with its own composition law. Let G prime be a group with its own composition law. And phi be a map from G to G prime such that for all x and y and G, this thing holds. That's a lot of stuff to pack into such a small space here. But that's nice because I'm working with not a lot of space here. So that's good for me. And it's also good for math. That's one of the main things about mathematics as a whole, is that you can talk, you use these symbols to talk about you can talk about a lot of things in a very short amount of time. It's sort of like how much information can you condense into a very small amount of notation. But anyway, so then phi of E equals E prime, and for all x and G, I'm going to write this. My board space is getting sloppy. I shouldn't do this, but I'm going to do it anyway. I'm going to write phi of x inverse equals phi of x inverse. So let's keep track of where these things are happening. This E is in G. This E prime is this E is the identity in G. This E prime is the identity in G prime. And of course, this inverse is in G. This inverse is in G prime. So let's prove this. So phi of E, well, E is the same as E times E. Then we use our what we know about group homomorphisms, and we can take this product in here and make it a product out here. And multiplying this equation by phi of e inverse yields, so let's see here, we have e prime is phi of e inverse phi of e is equal to phi of e inverse phi of e equals e prime is going to be equal to just phi of e, because what's going to happen here is that these two, this phi e inverse and phi e, are going to combine and give you e prime, and then we're multiplying e prime by phi of e, which is just phi of e. And of course, when I say multiplying this equation by phi inverse, it's this equation is going to become this equation. So here we've just tacked on, well, it's this equals this, and we've tacked it on here. So that's how that works. Okay, so that's that. And now we have to deal with inverses. See here. So next, e prime is, so let's actually say, so let's see here, for all x in g, so this is for all x in g, we have, what do we have? E prime is, well, we know it's phi of e, but e is phi of x times x inverse, because x times x inverse is e. So this is, but this is a group homomorphism, so this is phi of x times phi of x inverse. And we also have e prime is equal to, we do pretty much the same thing, but here we do x inverse times x. That's phi of x inverse, phi of x. Okay. So if phi of x times phi of x inverse and phi of x inverse times phi of x both equal e prime, then thus phi of x inverse must be the inverse of this phi of x. Or writing it another way, this is phi of x inverse. Because remember, that's exactly how we define the inverse. So let's do a remark. So we defined a group homomorphism between groups. But this really, there's no mention of inverses here. So you could imagine you could define a monoid homomorphism to be the same thing. And in fact you can. However, a monoid homomorphism, and I'm just going to write hom, needs not send e to e prime. So for an example, the natural numbers and 0. No. The natural numbers and... Oh, well, I guess earlier when I was writing, like, the notation, like, I wrote, and, like, I'd write the set, and I'd write the, composition law, and I would just leave it at that. Typically, you also can write the identity element here. So you'll have set, you'll have composition law, you'll have identity element. So we're going to let this be our monoid, and phi in hom from n to n be given by phi of n equals 0. So phi sends everything to 0. So it's obvious that this is going to hold because it sends everything to 0. Oh, no. This is our monoid. Multiplication. So you can sort of see this in your head, how multiplication is obviously associative, and if you multiply any two natural numbers together, you're going to get a natural number. That makes this a monoid. And so if we look at this map, it sends everything to 0. So this equation holds trivially because it's phi of blank is going to be 0, and then phi of blank times phi of blank, that's going to be 0 times 0, which is 0. So it's always going to hold. You don't even really have to think much about that. But yeah, it sends the identity, which is 1, to 0, which is not 1. Okay, we have another example here. I'm going to skip that. So now we're going to do another important definition. It's here. Let G be a group and H a subset of G. H is a subgroup if E is in H, we've also got X and Y in H will imply that X times Y is in H. This composition, of course, this product being the composition law in this group, in the group G. And if X is in H, then X inverse is in H. And we will write H is less than G to mean it's a subgroup. Now, this notation is a little annoying because obviously, or at least we'll see, any group is a subgroup of itself. And so you have sort of trivial subgroups. And so in particular, any subgroup could just be whatever group you started with. And so this wouldn't be a less than, this would be just an equal to. You can have H equal G. And so that kind of conflicts with our intuition of, oh, well, when we use less than in the past to talk about numbers, you can't have any number be less than itself. That's impossible. But here, every group is less than itself because every group is a subgroup of itself. Of course, you can fix that by writing less than or equal to if you're allowing H to be G. But if you want to say that, like, oh, H is a subgroup of G which is not G, then you just write H is strictly less than, like that. But people tend to just write less than, regardless of whether they mean less than or equal to or just less than. So typically if you see less than, this means H is a subgroup of G. It might be all of G, but it might not. So it can be a little annoying. Whatever. Okay, so that's what a subgroup is. So basically, a subgroup is a subset of a group, which itself is a group, because it contains the identity. It's closed under multiplication, and it's closed under inverses. When we say closed under multiplication, it means if you do multiplication within H, you stay in H. And closed under inverses means if you take inverses in H, you stay in H. That's just a kind of a common vernacular way that you talk about these things. Okay, so let's take an example of this. Let's see here. 0 plus minus 2 plus minus 4 as a subset of the integers is a subgroup, and I'll just say under plus, meaning where we take our group composition law to be addition. And that's kind of easy to see, because if you take any two even numbers and you add them together, you're going to get an even number. So, okay, let's actually check these. So E is in H, 0's in there, so we got it. If X and Y are in H, then is their product in H? Well, if you take two even numbers and you add them, you get an even number. So that's fine. How about inverses? Do we have inverses? We have plus or minus 0 because they're both 0, and we've got plus or minus everything else, and so we have inverses. So that's that. Okay, so here's another important definition. This one ends up, when you first see it, it looks really kind of weird, like, why would you come up with that? But this ends up being a really important concept in group theory. So this is something you really just have to sit down and memorize, because it's very important. A subgroup H of G is normal. So we call H a normal subgroup of G if for all A and G and for all B and G, no. B has to be in H. We have A, B, A inverse is in H. So, yeah, you start with an element of H, and then you surround it on both sides by an element A and an element A inverse, where A and A inverse are, or A is any element of our group G. This has to stay in H. It doesn't have to be, this doesn't have to equal B, but it has to be something in H. Then we write H triangle G when H is normal in G. Let's make an observation. If H is in G and G is abelian, then for all A and G and for all B and H, we've got ABA inverse. Well, this is abelian, so we can move that A across. And look, we have A times A inverse. By the way, I'm not being careful here when I write this product. I'm not using parentheses. I'm not telling you which product to do first. The point of associativity is that doesn't matter. That's something that you sort of have to prove, that if you have just a string of things that you're multiplying together in a group, it doesn't matter where you put the parentheses. You'll still get the same thing. That's something you have to prove. It doesn't take a lot of work, but it's a pretty standard thing, and you can find it in a lot of textbooks. I don't think we're going to go over it. So ABA inverse is BA A inverse equals B, which is in H. So H is normal in G. So for an abelian group, it's kind of boring. It doesn't really tell us anything useful. All right, so that's this, and we're actually nearing the end of this. I'm going to have to try to figure out some way to reduce the time I spend on these lectures, because this is taking a lot longer than it took to go over these in class. But I tend to err on the side of being overly thorough, so it just might be a personal thing. And the other nice thing about YouTube is that this isn't like a class. I'm not in a classroom trying to teach people. This is me posting YouTube videos. I can do whatever I want. So I can make these as long as I want, and it's fine. But, I mean, it's not fine if it's inconvenient for the viewers, but we'll work on this. So let's talk more about homomorphisms. So let phi be in hom G to G prime. So let G and G be groups, and phi a map from G to G, which has that composition law thing. We define the kernel of phi as the collection of X and G. Actually, this is going to take 2 lines, so I might as well write out the words so that you actually see them. Although this probably would be discussed in a linear algebra class, but the kernel of phi is written as ker phi, which is the collection of elements X and G, such that phi of X is E prime, the identity in G prime. And the image is written as M phi, and this is just the collection of all elements phi X where X is in G. So the kernel is a collection of elements. The kernel is a subset of G, which is the things that map to E prime. The image is a subset of G prime, which is the things which get mapped to under this map. And so we've got these 2 subsets. So you might think, oh, well, we just talked about subgroups and normal subgroups. Are they subgroups? Are they normal? So the answer is yes and sometimes. Lemma. So it turns out the kernel of phi is a normal subgroup of G, and the image of phi is just a subgroup of G prime. So this is really why normal subgroups are important. It's because kernels of homomorphisms are normal, and homomorphisms are really important. So anyways, let's prove this. Phi of E is E prime, right, because it's a group homomorphism. So, and we know that this always holds in a group homomorphism. So E is in the kernel of phi. So we've got the identity in there. What about closure under multiplication? If A and B incur phi, then we want A times B to be in the kernel of phi. So let's see what happens to phi of AB. Oh, well, we do the obvious thing where we break it up it becomes phi of A times phi of B. Oh, but look, A and B are in the kernel, and so phi of A is E prime and phi of E is E prime, and so this is E prime. So AB is in the kernel of phi. Okay, what about inverses? If A is in ker phi, let's see here, then what about this? Let's look at the phi of A inverse. Well, we proved as our lemma from earlier on, was it a lemma? We proved it in any case, that this is phi of A inverse. But phi of A is in the kernel, so this is this is E prime inverse. I had those parentheses there because I didn't want to put e to the 1 minus 1, because this is actually an E prime. So E prime inverse, but the inverse of the identity element is just the identity. Because you multiply the identity by itself, you get the identity. Okay? See here. Thus, kernel of phi is a subgroup of G. That doesn't tell us anything about normality. So, for normality, let's see here. Going to let A be in any element of G and B be an element of the kernel of phi. Sometimes I put the parentheses around phi, sometimes I don't. It doesn't really matter. So then phi of AB A inverse equals phi of A times phi of B times phi of A inverse. Actually, yeah, because we break up the 3 and then the inverse comes outside. And then this is really messy of me to break up this proof and have the proof start at the bottom half of the board and end on the top half of the board. But what I have to do. So it's going to equal, okay, well, phi of A is, okay, so A is in G, B is in the kernel of phi. So this is phi of A times, okay, so phi of B, since B is in the kernel, this is E prime, times phi of A. Actually, you know what? Yeah, let's keep that outside. Phi of A inverse. So of course this is going to be phi of A inverse, which is E prime. No, we want AB and we want ABA inverse. We want ABA inverse to be right. We want ABA inverse to be in phi, in the kernel of phi, and we know that phi maps ABA inverse to E prime, and so ABA inverse is in kernel of phi. And thus, kernel of phi is normal in G. Now, let's see here. For the image of phi, basically he said just to check this on your own. I didn't do it yet, but we're going to do it here. It shouldn't be hard.